Hello everyone, my name is Mridul. Today, me and my batchmates Mukul, Naman Bhatt, Naman Koel, Naman Kumar, Naman Manav are going to explain the first chapter of the Case Overview book, which is titled as Basic Principles. Before diving into that, I would like to give you a short info about principles. So, principles are nothing but a general scientific theorem or law that has numerous special applications across a wide field. In this chapter, we'll be learning various things about fluid flow machines, which are very broadly classified as turbo machines and positive displacement machines. Now, coming on to the turbo machines. Turbo machines are nothing but a device that adds energy to a fluid or extracts energy from the fluid. They are divided into two categories. They are called as pumps when they add some energy to it, and they are called as turbine when it attracts some energy. Their basic element is a rotor. These machines are called pumps, and if they add some energy, and if it extracts energy, it is called a turbine. However, there are two fluid machinery machine for different types of fluids, such as incompressible fluids and compressible fluids. So, the fluid machinery for compressible fluids is beyond the scope of this book. So, we'll be only discussing and looking into the incompressible fluid. As discussed a moment ago, we'll only be focusing on the incompressible fluid flow, water being the most widely used fluid for turbines. Chapters on the chapters on the book deal with turbines in water turbines, as water turbines reflect the behavior of most incompressible fluid flow pumps, and hence the attention of this book is confined essentially to the work to water as the working fluid. Our first topic is control volume. So control volume is denoted by CV, and it is a fixed volume in a space of the fluid flow field, while the boundaries of control volume doesn't change. The mass and energy can cross its boundaries. To understand this concept better, we will look at the figure 1.1, in which the A part shows the control volume in the case of impingement of a free jet on a flat plate. In this, a jet of liquid of density amounting to a discharge Q and having a velocity V impinges normally on a fixed plate. The control volume is shown in the figure. Now we'll look at figure B, the second figure is figure B, which shows the flows through a bend. The control volume that we should draw, the pressure, velocity, and at the two ends, the reaction force and R acting on the CV, and its complement is X and Y direction are shown in the figure. Now coming on to our next topic, which is linear momentum equation. You've all heard of the basic momentum equation, which is P is equal to mv, momentum into velocity. Now linear momentum is nothing but a vector quantity, and its equation is defined as the vector sum of all external forces acting on a control volume in a fluid flow, which is equal to the time rate of change of linear momentum vector of the fluid mass in the control volume. Now we have to differentiate what kind of external forces are acting on, and they can be boundary forces and body forces. Boundary forces are divided into FP and FB. FP rises due to pressure intensities acting normal to a boundary, and FB rises due to shear stresses acting tangentially to a boundary. Secondly, we have body forces, which are denoted by FB. These forces depend upon the mass of the fluid in the control volume. The linear momentum equation for a general flow can be written for any coordinate system as summation fx is equal to fpx, which plus fbx is equal to delta by dt delta t mx cv plus mx out minus mx in, which is the first equation, where mx is equal to the momentum flux in x direction, which is equal to rho q v. In this, as usual, rho is equal to density of the fluid, q is equal to discharge, and v is equal to velocity of flow. Suffixes out represent momentum flux going out the control volume, and n represent the momentum flux coming into the control volume. Similarly, suffix x represent the x component. Fpx, Fsx, and Fbx represent respectively the x component of a pressure force and shear force and body force acting on the control volume. Delta by delta T mx Cv is equal to rate of change of x momentum within the control volume. This component is zero for a steady flow, which is quite understood. Thus, for steady fluid flow, the linear momentum equation in x direction is summation fx is equal to fpx plus fsx plus fbx is equal to mx out minus mx in, which is equal to rho q vx out minus rho q vx in. Similarly, momentum equation are applicable to other coordinate direction y and z also. Use a steady state linear momentum equation illustrated in the following jet impingement situation. The equation that we studied in the last topic will be illustrated in the following jet impingement situation, which brings us to impingement of free jets, our topic. A total of seven Seven jet impingement cases are discussed in the book. So we'll be looking at the first two. So first case, which is jet impingement on a stationary plate. We'll consider a circular jet of water striking a fixed plate inclined at an angle theta to the axis of jet as given in the figure 1.2. So this figure 1.2. The impinging jet is a free jet, that is the pressure is atmospheric in any cross section of the jet, and the ambient pressure is also atmospheric. The plate is assumed to be frictionless. Now we'll be considering a control volume, as we have already considered a surface on which it will be acting. The velocity of jet u is equal to v, and its cross-sectional area is equal to a, and its discharge is equal to q. The pressure on surface of CV is atmospheric, and the jet strikes the plate and spreads tangentially or radially to the face of the plate. As there's no friction at the plate, the velocity of the flow at any tangential direction is constant at a value of v. Thus, in any tangential direction, there is no change in momentum flux. By linear momentum equation, there is no reaction force on the control volume, and hence there is no tangential force on the plate. Now, looking at figure 1.2, let Rn be the reaction force in normal direction. The force on the plate is in normal direction is equal to Fn, which is equal and opposite to Rn. While the velocity entering the control volume in normal direction is v sine theta, the velocity leaving the control volume in normal direction is v sine theta, and the velocity leaving in control volume is zero. Thus, the equations concerned with this kind of situations are sigma forces in n direction is equal to moment of flux in n direction out minus momentum flux in n direction in, which is 0 minus Rn is equal to rho q into 0 minus rho qv into sine theta, which is the third equation. Rn is equal to rho qv sine theta. Thus, the normal force on the plate is Fn, which is equal to rho qv sine theta, the positive n direction, that is in the direction of the jet. Then the tangential force on the control volume Ft, which is equal to 0. So the total force on the plate is F is equal to Fn, which is rho qv sine theta, which gives us our fourth equation. The plate is stationary, and as such, the force on the plate does no work. When theta is equal to 90 degree, the case refers to the normal impingement of free jet on a plate. In that case, the total force on the plate is F is equal to rho qv in the direction of jet. So now coming on to the second case, which is jet impingement on a moving plate. So here, in this case, the jet impingement is on a moving plate. In this case, the plane of the plate is inclined at an angle theta also to the jet, and the plate is moving with the velocity u in the direction of the jet. Now, looking at figure 1.3, A part. Notice that there is a relative motion between the jet of water and the plate. The jet has a relative velocity of v minus u with respect to the plate. Hence, to proceed further, we will consider a velocity of magnitude minus u, which is equal and opposite to the velocity of the plate. Now, being superimposed on the flow system, the resulting flow situation, which can be called as the equivalent relative flow over the plate, is given in figure 1.3b. In this, the plate is relatively stationary, and the jet is having an area with the relative velocity of v minus u. So its relative discharge is given by qr, which is equal to a into v minus u. Here, as we studied, the plate is relatively stationary and the jet is an area of A and relative velocity. So we all discussed this. Now notice that in the last equation. Now recall the flow situation which we discussed in case A. This relative flow situation is similar to that only, as there is no tangential flow on the plate, and the normal force on the plate Fn is given by Fn is equal to rho q r v minus u sine theta is equal to rho u v minus u whole square sine theta. Also, the component of the velocity of the plate in the normal direction is un is equal to u sine theta. Now, the normal force which is given by Fn moves with the velocity un, and hence the rate of work done on the plate is equal to power transmitted to the plate. P is equal to Fn u sine theta, which is equal to rho a v minus u whole square u sine square theta. Now, K is supplied by the jet. The kinetic energy supplied by the jet per unit time is given by half rho a v into v square. And the efficiency of power transmission is given by power transmitted to the plate upon kinetic energy supplied by the jet per unit time. So, which is equal to rho a v minus u whole square u sine square theta upon half rho a v into v square, which gives us 2 v minus u whole square u sine square theta upon v cube. Now, notice that in the last equation, if theta is a variable, the efficiency is maximum at theta is equal to 90 degree. That is normal impingement on the plate. Also, in this flow situation, movement of the plate causes the distance between the nozzle and the plate to continuously increase with time. Hence, this is not a practically feasible flow situation.
Good morning, everyone. My name is Mukul. My roll number is 2K20 ME162. I'm here to present some cases of impeachment of free jets. Without further ado, let us discuss about these cases. Now, these cases are the first cases which was a jet impingement on a set of a flat plates mounted on a wheel, and the second case is jet impingement on a stationary curved plate. Third one, the jet impingement on a single moving symmetric curved plates, and the fourth, the jet impingement on a series of a curved vanes mounted on a wheel. The first case, which is the jet impingement on a set of a flat plates mounted on a wheel. Now let us consider a set of mounted radically on a wheel that is capable of rotating about its axis in a figure. The figure is in the next slide. Now the free jet of water strikes the plates, and as the wheel moves, one plate or another intersect the jet continuously. If the sufficient number of plates is properly assembled, these plates mounted on a rotating wheel can intercept the entire discharge from the jet. Let V the velocity of the jet of a cross-sectional area A, and U is equals to peripheral velocity of the wheel. For a single plate, the flow situation is similar to the case discussed earlier. However, when all the plates of a wheel are considered, one or another vanes will intercept all the flow from the jet. Thus, the entire discharge issuing out from the jet involves the transfer of power to the wheel, while the relative velocity of plates is still is which is equals to V minus U, and the total discharge which is equals to AV, which is area into velocity. In the involved momentum flux undergoing the change is not require relative discharge, which is QR, as in the case B. The jet impinges normally on the plate with making of angle theta 90, and the plates move with a velocity u after the impact. Now let's see, this is the wheel which is properly placed with the jet, and the jet which is striking the plates with the help of their flow. And as discussed earlier, the what the thing was, when the jet strikes the plate, suddenly second plate appears, and this process will go on further and further, and the wheel tries to spin on the axis of their rotation. Now the problem reduces to the case of normal impingement of a free jet discharge. The q is which is equals to av, having the relative velocity which is v minus u on a relative stationary plate. This is similar case which is b within angle of 90 degrees. Let Rx is equal to x minus component of the reaction of the plate on the control volume, which is minus rho av and bracket v minus u, which is the relative velocity. The idealized force Fx is equals to the opposite to Rx. Okay, thus the idealized force on the plate in the x direction, and Fx is which is equals to rho Av, or and the into relative velocity. Assuming all the losses which are zero, the rate of work done by the assembly of plates which is equals to power transmitted to the wheels. Now the power which is F into U, which is rho av into relative velocity into the velocity which after the strike of the jet, which is u. Okay, the kinetic energy supplied by the jet per unit of time, which is half rho av into v square. Okay, now the efficiency of power transmission, which is equals to obviously power transmitted to the wheel upon kinetic energy supplied by the jet per unit time, which is 2. Now this is the second case, which is jet impingement on a stationary curved plate. Okay, the figure shows a two-dimensional free jet of cross-sectional area A impinging at the center of the symmetric stationary curved plates with a velocity of v. The jet is at atmospheric pressure, and the pressure on the boundaries of the control volume is also atmospheric. Now the flow is assumed frictionless, and hence the jet leaving the vane will have the same velocity as v as the impinging jet. the jet splits symmetrically on the either side of the impingement of plane, the flow exiting on the vane making an angle theta with the negative direction of the x-axis, and the deflection angle of the jet which is 180 degrees minus theta, and the discharge impinging on the jet which is also area into velocity which is av. Let rx is the x component of the reaction of the vane on the control volume, and the ry is also y component of the reaction of the vane on the control volume. Okay, considering the linear momentum equation in the x direction of the control volume, which is summation of forces in all x direction, which is equals to momentum flux in x direction out and minus momentum flux in the x direction inlet. Okay, the further 0 minus rx which is equals to minus rho av v cos theta minus rho av into v, which is represented as rx is equal to rho av square plus 1 plus cos theta. Okay, now do further. This is the image which is showing that the velocity curve plate is situated on the center, and the jet is implying water, and the water gets separated from the right to the right and the left direction. Okay, now the fx be the force on the vane in the x direction, which is fx is also equal and opposite to rx. Okay, and this is represent this as rho into av square plus 1 plus cos theta acting on the positive direction of the x by linear momentum equation in the y direction. Now the summation of forces in y direction is also equals to momentum in flux y direction out minus momentum flux in x direction in, which is also similar to the forces in direction x. Okay, now the ry is equals to rho into av into v sin theta plus minus rho av v sin theta minus 0, which is equals to 0. Hence the ry, the force of the vane in the y direction, is 0. Now further do with the jump impingement on a single moving symmetric curve plate. This is the third case we are listening, the which is the flow is similar to the last case, accepting the fact of the blades itself moving along with the jet with a velocity u, and a two-dimensional jet impinges on the axis of the curved plates and splits symmetrically either on sides. Okay, as in case b, the flow situation relative to the stationary vane is considered. For this, a velocity equals and opposite to u, which is impressed on the jet as well as on the curved plates. Now the resulting flow situation is shown in the figure, like there is a figure. Now the deflection angle of the relative velocity of the jet, which is 180 degree minus theta, obviously the curved plates on the relative stationary, the incoming jet has relative velocity of vr, which is v minus u, as we know, and the cross-sectional area of A. As there is no friction in the flow over the vane, the exit relative velocity from the vane, which is Vr minus U, and the same impingement relative velocity of x on the jet. Each of the relative flows exiting the vane makes an angle theta with the negative direction of x-axis. The relative discharge is QR into A into V minus U. Okay, now the relative discharge which is takes place in there, which is the area of the jet into the velocity, which is relative velocity, are showing here. Okay, now it can now be observed that the relative flow situation is similar to the case d last we studied about that. Now the let x component of the reaction of the vane controlled volume similar to the last case, and the ry component ry which is equals to y component of the reaction of the vane in the on the control volume. Okay, considering the linear momentum equation of the in x direction. Okay, now the similarly from the last case, there is a summation of forces in all x directions. Now the which is also similar momentum in flux direction x outlet, and the minus momentum on flux in direction x inlet. Okay, now the Rx, which is equals to rho A bracket relative velocity, relative, uh, what was that? Let me, relative velocity. Okay, sorry, I forgot it. Relative velocity square into 1 plus cos theta. Now the second thing was if the Fx be the force on the vane in the x direction, Fx is also equal and opposite to the Rx, hence given by, which is equals to Fx is equals to rho A relative velocity square of relative velocity into 1 plus cos theta acting on the positive direction by the linear momentum equation in the y direction. Now similarly for the y direction, which is also like 0, hence Ry is the force on the vanes in y direction is 0. Work done by the jet per second is equal to power transferred to the vane. Okay, now the work done power is equals to rho a relative velocity square into u into 1 plus cos theta. Okay, now the kinetic energy supplied by the jet per unit time, which is equals to 1 by 2 rho av into v square. Now the efficiency of the system is also, you know, that the power transmission of the vane upon the kinetic energy supplied by the jet per unit time, which is equals to rho relative velocity square u plus 1 plus cos theta, which is equals to 2 v square 2 into bracket v minus u square u into bracket 1 plus cos theta upon v3. Thank you.
Hello everyone, my name is Naman Bhatt, roll number 2K20ME163, and I am here to explain the Reynolds transport theorem. The introduction. Reynolds transport theorem is a theorem which is used to relate statement of any physical law to a system to the statement of that physical law to a control volume. This means that the sum of the rate of change of property per unit time for a control volume and rate of efflux of the property are equal to the rate of change of extensive property of the system with respect to time. The Reynolds transport theorem is something extremely important in the formulation of basic laws of fluid dynamics, which are the mass conservation equation, momentum conservation equation and energy conservation equation. तो रेनॉल्ड्स ट्रांसपोर्ट थ्योरम बेसिकली जो है ये हमें ये बताता है कि जितना भी रेट ऑफ चेंज ऑफ प्रॉपर्टी हो रही है फ्लूइड की, बी इट वो उसकी स्पीड हो या बी इट वो उसकी डेंसिटी हो या बी इट उसकी फ्लूइड प्रॉपर्टी हो, ये जितना भी चेंज करता है ये रेट ऑफ चेंज ऑफ एफ्लक्स को अफेक्ट करता है. जितनी भी प्रॉपर्टी चेंज होती है वो एक स्ट्रीमलाइन उसका जितना भी उसका फ्लो का प्रॉपर्टी होता है उसको मेंटेन करने के लिए दैट शिफ्ट्स अकॉर्डिंग टू इट. तो जो भी होता है वो कांस्टेंट रहता है. तो ये है जैसे कि हमारे सामने जनरलाइज फॉर्म ऑफ रेनॉल्ड्स इक्वेशन है. जैसे कि आप देख सकते हैं वी हैव टेकन अ पार्ट ऑफ अ सिस्टम एंड उसके रिस्पेक्ट में हम इंटीग्रल लेके हम इसकी इक्वेशन बनाते हैं. दिस इक्वेशन कैन वेरी फ्रॉम सिस्टम टू सिस्टम एंड कंडीशन टू कंडीशन, बट जो हमारे कॉन्स्टेंट्स होते हैं एंड ऑल द यूनिट्स विच रिप्रेजेंट they are probably same for every equation, where eta stands for the intensive property related to the extensive property, n is per unit mass, t represents the time, cv represents the control volume, cs represents the control surface, rho represents the fluid density, v represents the volume, Vb represents the velocity of the boundary of control volume, the control surface. Vr represents the velocity of fluid with respect to control surface. N represents the outward pointing normal vector on the control surface. And A represents the area. तो ये कुछ important points है जो हमको याद रखने होते हैं whenever we solve a question through RTT. A particle is a differential concept of the system because we take the particle as कि जिसमें पूरा सिस्टम हमारा समाया हुआ होता है. जैसे कि हम पूरे सिस्टम को एक साथ नहीं ले सकते तो वी जस्ट टेक अ पार्ट ऑफ दैट्स कॉल्ड अ पार्टिकल, एंड उस पार्टिकल के बेसिस पे उसकी प्रॉपर्टी के बेसिस पे वी एनालाइज द सिस्टम. तो एनीथिंग डिफाइंड विद रिस्पेक्ट टू द सिस्टम, एंड जितना भी पार्टिकल्स हम एनालाइज करते हैं वो सिस्टम के रिस्पेक्ट में हम डिफाइन करते हैं. जितने भी बेसिक लॉज होते हैं सिस्टम के वो फर्स्ट इनिशिएट किए जाते हैं. जितना भी फोर्स से रिलेटेड लॉज होते हैं या मास कंजर्वेशन से वो लगाए जाते हैं. बट लेटर जो था वो डिफाइन किया गया था बेसिक लॉज विद रिस्पेक्ट टू कंट्रोल वॉल्यूम, बिकॉज कंट्रोल वॉल्यूम कैन बी अप्लाइड टू एवरी केस, बिकॉज मोस्टली केसेस में इट इज़ मोर एक्यूरेट एंड हेल्पफुल रहता है, एंड वॉल्यूम इज़ मोस्टली कॉन्स्टेंट। तो कॉन्सेप्ट जो है सिस्टम का, मास एंड बाउंड्री आर इम्पॉर्टेंट कॉन्सेप्ट्स ऑफ द सिस्टम, बिकॉज एक सिस्टम को एक मास और एक बाउंड्री ही बनाता है। जो बाउंड्री के अंदर मास होता है, दे बोथ कंबाइन एंड मेक अ सिस्टम इन विच वी एनालाइज एंड हम एक कॉन्सेप्ट बनाते हैं जिससे हमें अपने प्रॉब्लम्स को सॉल्व करने में हेल्प मिलता है। The first physical principle to which we apply the relationship between system formulations and control volume is the mass conservation principle. Because fluid एक जगह से दूसरी जगह जाता है without any loss, if we consider an ideal case, तो हमारा mass always conserved रहता है। जो mass होता है system का वो हमेशा constant रहेगा। It can be concluded that the product of density by the input area and the input speed is equal to the density times the output area and output speed. Such a condition leaves the flow in equilibrium, दैट इज द इनपुट फ्लो इक्वल्स टू आउटपुट फ्लो। ये हमने लास्ट इक्वेशन में पढ़ा था आरटीटी की, जो हमने डिराइव करी थी। तो ये हमारे टाइप्स ऑफ सिस्टम होते हैं, कंट्रोल वॉल्यूम सिस्टम और ओपन सिस्टम, देन वी हैव द कंट्रोल मास सिस्टम और क्लोज सिस्टम, एंड देन वी फाइनली हैव द आइसोलेटेड सिस्टम। तो ये जो तीन तरह के सिस्टम्स होते हैं, ये हमें केसेस बताते हैं, एंड हमें केसेस को इन सिस्टम्स के अकॉर्डिंग डील करना पड़ता है। कोई ओपन सिस्टम होता है जिसमें एनर्जी लॉसेस होते हैं, एंड वी हैव अ क्लोज सिस्टम जिसमें कुछ भी नहीं होता, एंड देन वी हैव एन आइसोलेटेड सिस्टम विच इज आइसोलेटेड फ्रॉम एवरीथिंग। इसमें ना इनवर्ड फ्लो होता है ना आउटवर्ड फ्लो होता है, एंड दिस सिस्टम इज आइसोलेटेड इन इट्स ओन। ना कोई चीज़ अंदर जा सकती है ना बाहर जा सकती है, बी इट मास और बी इट एनीथिंग एल्स। तो इन तीन तरह के सिस्टम्स पे हमको कंजर्वेशन एंड ऑल हमारे प्रिंसिपल्स लगाने पड़ते हैं क्वेश्चंस में, एंड व्हेनेवर वी सॉल्व अ प्रॉब्लम। तो जो हमारा फर्स्ट सिस्टम है वो है कंट्रोल वॉल्यूम सिस्टम और हमारा ओपन सिस्टम। तो कंट्रोल मास सिस्टम, मास ट्रांसफर जो होता है वो इस सिस्टम में अलाउड नहीं होता। जितना मास हमारा वाटर का रहता है या फ्लूइड का जो भी रहता है वो हमें ट्रांसफर करना अलाउड नहीं होता। दैट कांट गो आउट ऑफ द सिस्टम, नाइदर कैन एनीथिंग एल्स एंटर इन द सिस्टम। आइडेंटिटी जो होती है सिस्टम की वो कांस्टेंट रहती है। द आइडेंटिटी सेम्स कांस्टेंट of the system. Boundary may contract or expand as energy transfer is allowed, so the boundary is flexible. So ये flexibility इसीलिए आती है क्योंकि energy transfer हो रहा है आगे से बाहर एंड अंदर से बाहर। तो जितना भी हीट अप होता है, एक्सपेंशन होता है, उस एक्सपेंशन की वजह से हमारी बाउंड्री फ्लेक्सिबल रहती है, एंड दैट कैन एक्सपैंड और दैट कैन कॉन्ट्रैक्ट। एंड जो आइडेंटिटी होती है वो कांस्टेंट रहती है। जो सिस्टम की आइडेंटिटी, मेन आइडेंटिटी होती है, वो चेंज नहीं होती। जितना भी रहता है सिस्टम की प्रॉपर्टीज वो दैट विल बी सेम। नेक्स्ट वी हैव द कंट्रोल वॉल्यूम सिस्टम। इट इज ऑल्सो नोन एज द ओपन सिस्टम। ये इस काइंड ऑफ सिस्टम में मास और एनर्जी जो होता है वो बोथ टेक प्लेस लेते हैं, दे बोथ आर एक्सचेंज्ड, एंड जो आइडेंटिटी होती है सिस्टम की वो लॉस हो जाती है। बिकॉज ये काफ़ी इनएविटेबल एंड नेचुरल सी बात है, क्योंकि अगर दोनों का चेंज ऑफ प्लेस लेगा, बी इट मास और बी इट एनर्जी, व्हेन बोथ आर एक्सचेंज, नेचुरल सी बात है कि सिस्टम की आइडेंटिटी लॉस हो जाएगी, विच वॉज देयर अर्लियर, दिस दैट इजंट लेटर। एंड जितना भी हमारा एनालाइज किया था हमने सिस्टम, दैट कैन वेरी ओवर टाइम, एंड दैट विल वेरी फ्रॉम एंड टू एंड, बिकॉज हर मोमेंट कुछ ना कुछ एनर्जी चेंज हो रही है, मास चेंज हो रहा है, एंड द सिस्टम इज गेटिंग काइंड ऑफ रिफ्रेश्ड एवरी टाइम। जो बाउंड्री होती है वो रिजिड होती है, एंड देयर इज नो चेंज ऑफ शेप दैट टेक्स प्लेस, बिकॉज ये चीज़ अंदर ही अंदर रहती है। दिस इज एन इंट्रिंसिक प्रोसेस, एंड जितने भी चेंज ऑफ शेप होती है दैट डजंट टेक प्लेस। After that, we have the isolated system. In an isolated system, no mass transfer or no energy takes place. It is isolated from all the surroundings. जैसे कि हमारे पुराने केसेस में होता है कि हमारा जो मास ट्रांसफ़र होता है that takes place, एंड किसी केसेस में हमारा एनर्जी ट्रांसफ़र टेक प्लेस रहता है, एंड कभी कभार हमारी जो बाउंड्रीज होती है दैट कॉन्ट्रैक्शन दैट एक्सपैंड्स, बट सम केसेस में वो भी रिजिड होती है, बट वो भी नहीं करती। इन एन आइसोलेटेड सिस्टम हमारे पास ये होता है कि इसमें हमारा ना बाउंड्री कॉन्ट्रैक्ट एक्सपैंड करती है, ना हमारा मास एक्सचेंज होता है, ना हमारा एनर्जी एक्सचेंज होता है, एंड यहाँ पे प्रोसेसेस ना इनवर्ड होते हैं ना आउटवर्ड होते हैं. दिस इज एन एक्सट्रीमली कांस्टेंट सिस्टम. ये लाइक दिस इज द मोस्ट आइडियल केस ऑफ अ फ्लूइड सिस्टम जिसमें हमारे पास कुछ भी नहीं रहता एंड ना कुछ आता है ना कुछ जाता है उसके अंदर से. तो एन आइसोलेटेड सिस्टम इज अ सिस्टम ऑन इट्स ओन. एग्जाम्पल ऑफ कंजर्वेशन ऑफ मास जैसे कि आपके सामने कंसिडर फॉर अ सिस्टम. इसमें रेट ऑफ चेंज ऑफ मास जो है वो कांस्टेंट है. जैसे कि आप देख सकते हैं dm/dt, द रेट ऑफ चेंज ऑफ मास विद इन अ सिस्टम, दिस इज जीरो. इट रिमेन्स कांस्टेंट इनसाइड द सिस्टम. बट अगर वो चीज़ अब हम कंट्रोल वॉल्यूम के लिए कंसिडर करें, continuity equation states that the net rate of increase in mass in the control volume plus net rate of mass of efflux of the control volume equals to zero. तो कंट्रोल वॉल्यूम के केस में हमारे पास ये हो जाता है कंटिन्यूटी इक्वेशन के हिसाब से जो नेट रेट ऑफ चेंज इन मास होता है कंट्रोल वॉल्यूम का प्लस द नेट रेट ऑफ चेंज ऑफ मास एफ्लक्स ऑफ कंट्रोल वॉल्यूम वो जीरो रहता है. जीरो एज इन द डिफरेंस रिमेन्स जीरो एंड विच स्टेट्स दैट इट ऑलवेज रिमेन्स कॉन्स्टेंट. तो ये जो कंसिस्टेंसी है हमारी कंट्रोल वॉल्यूम की वजह से आती है because mass constant है and this shows us that the mass always remains constant in a flow and in a process. Thank you.
Hello everyone, my name is Naman Goyal and I am in Delhi Technological University, currently in third year pursuing mechanical engineering. My roll number is 2K20ME164 and this project is based on velocity triangles and is submitted to our teacher, Mr. Rajkumar Singh. So first of all, we'll begin with what exactly is a velocity triangle. Velocity triangle होता क्या है? Velocity triangle एक ऐसा triangle होता है जिसके अंदर जो हमारा fluid होता है, fluid के velocity के different components को represent करने के लिए use किया जाता है. वेलोसिटी ट्रायंगल जो होता है वो इनलेट और आउटलेट सेक्शन दोनों के लिए अलग अलग होता है और हम उसको दोनों के लिए इजीली हम ड्रॉ कर सकते हैं. एंड द मोस्ट बेसिक फॉर्म ऑफ अ वेलोसिटी ट्रायंगल कंप्राइजेस ऑफ थ्री वेलोसिटीज व्हिच आर टेंजेंशियल वेलोसिटी, relative velocity and absolute velocity, and these three velocities combine together to form the velocity diagram which we better known as velocity triangle. So coming on to the next thing, that why do we need velocity triangle? वेलोसिटी ट्रायंगल की ऐसा क्या था जो हमें उसकी जरूरत पड़ी? सो दीज वेलोसिटी ट्रायंगल्स आर यूज्ड टू इलस्ट्रेट द फ्लो कंडीशंस. द कॉरेस्पॉन्डिंग स्टेटस ऑफ द फ्लो इज डिस्क्राइब्ड बाय द फ्लो वेलोसिटीज. These are used extensively in the analysis of the flow across the runners of the turbines and impellers of pumps. These velocity triangles help us in the visualizing of flow in a graph notation and in the derivation or application of appropriate trigonometric relations. All these things can easily be done by the velocity triangle. Okay, so next thing, that for construction of the velocity triangle, we'll consider a series of curved vanes mounted on a wheel. Wheel जो है अपनी एक्सिस पे constantly rotate करेगा at a constant speed. Water वेन पे enter करेगा at the inlet section और exit करेगा outlet section से. इसके हम डायग्राम जब हम इसका ड्रॉ करते हैं तो कुछ नोटेशंस हैं जो हम यूज करते हैं. तो यहाँ पे हम देखते हैं कि ये हमारी एक कर्व्ड प्लेट है. ये हमारी एक कर्व्ड प्लेट हो गई जो कि हमारी यू वेलोसिटी से मूव कर रही है. नोजल से पानी इंजेक्ट होगा वेन के ऊपर. नोजल पानी v1 वेलोसिटी से इंजेक्ट करेगा जिसको हम बोलते हैं एब्सोल्यूट वेलोसिटी. v1 वेलोसिटी के साथ वो वेन पे इंजेक्ट करेगा. हमारा वेन u वेलोसिटी से मूव कर रहा है. सो v1 वेलोसिटी ये हो गई, u हमारा ये वेलोसिटी हो गई. u1 जो है वो एब्सोल्यूट वेलोसिटी के साथ जो एंगल बनाएगा हॉरिजॉन्टल डायरेक्शन में उसको हम बोलते हैं अल्फा, विच वी बेटर नोन एज गाइड ब्लेड एंगल. u1 को हम बोलते हैं पेरिफेरल वेलोसिटी ऑफ द वेन. v हो गया हमारा एब्सोल्यूट वेलोसिटी, अल्फा हो गया हमारा गाइड ब्लेड एंगल. और वेलोसिटी ट्रायंगल को कंप्लीट करने के लिए जो थर्ड लाइन है जो हम b से c को ज्वाइन करेंगे उसको हम vr1 से बोलते हैं, डिनोट करते हैं. और इसका नाम होता है रिलेटिव वेलोसिटी ऑफ द ट्रायंगल. इनलेट पे इसको हम vr1 से डिनोट करते हैं और आउटलेट पे इसको हम vr2 से डिनोट करते हैं. और वेक्टर एडिशंस का यूज करते हुए vr1 इक्वल हो जाएगा v1 माइनस u1 के. और जो रिलेटिव वेलोसिटी है ये हॉरिजॉन्टल के साथ जो एंगल बनाएगी vr1 और u1 के बीच में जो हॉरिजॉन्टल डायरेक्शन में जो एंगल होगा उसको हम थीटा बोलते हैं जो हमारा ब्लेड एंगल होता है. तो ये देन फर्दर आता है VW1 और VF1। VW1 जो है V1 का ही हॉरिजॉन्टल डायरेक्शन में कंपोनेंट है, सो VW1 इज इक्वल टू V1 cos अल्फा। और VF1 जो है वो V1 जो एब्सोल्यूट वेलोसिटी है उसका टेंजेंशियल डायरेक्शन में जो कंपोनेंट है, जिसको हम V1 sin अल्फा भी बोल सकते हैं। तो यहाँ पे हमारे वेलोसिटी ट्रायंगल जो है कंप्लीट हो जाता है। सो यहाँ पे हम देख भी सकते हैं कि इन टर्बो मशीनरी अ वेलोसिटी ट्रायंगल is a triangle which represents the various components of velocities of the working fluid in turbo machine. तो ये हमने यहाँ पे डिनोट कर दिया, V is the absolute velocity of water, VR is a relative velocity, U is the peripheral velocity, alpha जो है हमारा वो angle made by the absolute velocity vector with the direction of peripheral velocity, जो मैंने बताया था कि जिसको हम बोलते हैं guide blade angle। B हमारा बीटा हो गया, जो हमारा angle made by the relative velocity and the flow peripheral velocity का हॉरिजॉन्टल डायरेक्शन में। ठीक है, तो हम जब नेक्स्ट पे जाते हैं, कंस्ट्रक्शन की हम बात करते हैं, तो यहाँ पे हमारा होगा कि रिलेटिव वेलोसिटी VR इट इज द डिफरेंस। रिलेटिव वेलोसिटी का मैंने भी बताया था कि हम जो वेलोसिटी ट्रायंगल हमारा होता है उसमें हम वेक्टर एडिशन का जब यूज करेंगे तो VR जो होता है वो V1 माइनस U1 के इक्वल हो जाएगा। सो रिलेटिव वेलोसिटी इज द डिफरेंस बिटवीन द एब्सोल्यूट वेलोसिटी ऑफ द फ्लो एंड द वेलोसिटी ऑफ द वेव। वेक्टर नोटेशन में इसको डिनोट करते हैं, हम बोलेंगे कि V1 V माइनस U इज इक्वल टू VR हो जाएगा। हमारा जो वेलोसिटी ट्रायंगल है उसको हमने कैसे किया था, एक ए से सी को ज्वाइन किया था जो एब्सोल्यूट वेलोसिटी को डिनोट कर रहा है, ए से हमने यहाँ पे बी को ज्वाइन किया था जो कि हमारा ये पेरिफेरल वेलोसिटी है, और फाइनली जो हमने बी से हमने सी को ज्वाइन किया था जो कि हमारी रिलेटिव वेलोसिटी हो जाएगी। सो ज्वाइन ए सी विच रिप्रेजेंट द एब्सोल्यूट वेलोसिटी वी। ठीक है, उसके बाद फर्दर जो होता है इसमें ABC ट्रायंगल इज नोन एज अ वेलोसिटी ट्रायंगल। इफ द वेलोसिटी वेक्टर refers to the inlet of the vein, then ABC is known as the inlet velocity triangle। Obviously जब वो जेट जो है हमारा उस जब वेन पे आ रहा होगा तो जब आने के लिए होगा तो वो इनलेट वेलोसिटी होगा, और जब वो एग्जिट कर रहा होगा बाहर से तो उसको हम आउटलेट बोल देंगे। तो सो इफ द वेलोसिटी वेक्टर्स रेफर टू द आउटलेट फ्रॉम द वेन देन ABC is known as the outlet velocity triangle। ठीक है, सो द नेक्स्ट थिंग in the triangle ABC the angles made by the absolute velocity with the peripheral velocity CAB is known as the guide vane angle, और जो एंगल हमारा रिलेटिव वेलोसिटी के साथ होगा उसको हम पेरिफेरल वेलोसिटी से होगा वो एंगल उसको बोल देंगे हम ब्लेड एंगल। ठीक है, तो अब जो हमारा ये एंगल होता है ये 3 तरह से हो सकता है। ये 90 डिग्री से ज़्यादा भी हो सकता है, इसको हमने डिनोट किया हुआ है, डायग्राम में शो किया हुआ है। वेलोसिटी ट्रायंगल में जो हमारे एंगल है ये 90 डिग्री से ज़्यादा भी हो सकता है, इक्वल टू 90 डिग्री भी हो सकता है, और 90 डिग्री से कम भी हो सकता है। यहाँ पे जो है एक्यूट एंगल बन जाएगा, इस केस में राइट एंगल बन जाएगा, और इस केस में जो एब्सोल्यूट बन जाएगा, ऑब्ट्यूज बन जाएगा, सॉरी। सो फिगर 1.8 में ऑब्ट्यूज एंगल ट्रायंगल हो गया, फिगर 1.9 में राइट एंगल ट्रायंगल हो गया, फिगर 1.10 में एक्यूट एंगल ट्रायंगल हो गया। सो जब एंगल्स डिफरेंट होंगे ग्रेटर देन π/2 और इज इक्वल टू π/2, तो उस केस में हमने रिलेशनशिप बनाया VF जो कि हमारा फ्लो वेलोसिटी था, एब्सोल्यूट वेलोसिटी का टेंजेंशियल कंपोनेंट, और VU जो कि हमारा प्लेट की पेरिफेरल वेलोसिटी थी। उन दोनों के बीच में हम लोगों ने रिलेशनशिप बनाया, बीटा when is greater than π/2 and when beta is equal to π/2। सो ये फॉर्मूला हो गया VF is equal to VR sin beta which is equal to V sin alpha, और VR उस केस में V sin alpha ही रहेगा, और VU जो है वो U plus VR cos beta dash हो जाएगा, और V cos alpha जो है U के इक्वल होगा। मूविंग ऑन टू द नेक्स्ट स्लाइड, यहाँ पे हमारा नेक्स्ट टॉपिक है कि देन टेंजेंशियल जेट इम्पिंजमेंट ऑन अ मूविंग वेन। So the impingement of a free jet of water on a moving curved vein at the edge of the vein is treated under 2 categories। इसमें जो हमारा जो जेट की impingement होती है वेन के ऊपर वो दो केसेस में डिवाइड करा, when the vein is single, और जो वेन है वो एक सीरीज ऑफ वेन्स में डिवाइड है। तो सिंगल मूविंग वेन जो हमारा केस बना उसको हम डिस्क्राइब करते हुए हम ये बोलेंगे, द फिगर में मैं आपको भी दिखाता हूँ। A free jet of water of area A and velocity V1 impinges tangentially at the edge M of the vein। For the shockless entry, the direction of the tangent to the blade at the entry M shall be the same as the direction of the relative velocity at its entry। तो ये हमारे इसके 3 केसेस हो जाएंगे यहाँ पे भी। आउटलेट व्हेन ग्रेटर देन 90 डिग्री, आउटलेट इज इक्वल टू 90 डिग्री एंड आउटलेट इज लेस देन 90 डिग्री। तो यहाँ पे हमारी वेन आ गई जो कि U वेलोसिटी से मूव कर रही है, हमारा ये इनलेट का यहाँ पे हमारा इनलेट का हो जाएगा। तो इसमें जब हम फर्दर देखेंगे तो आउटलेट के जो है एंगल्स 3 केसेस में हो गए। So in this case, this tangent makes an angle β1 with the negative direction of the velocity U, and this angle is known as the inlet blade angle। So यहाँ पे हमारा वही होगा कि जो relative velocity होगी वो absolute और peripheral velocity का subtraction होगा, उनका difference होगा। V1 अगेन हमारा एब्सोल्यूट वेलोसिटी है। इनलेट पे V1 जो है हमारा इनलेट पे होगा, V2 आउटलेट पे हो जाएगा। एब्सोल्यूट वेलोसिटी VR1 इज द रिलेटिव वेलोसिटी एट द इनलेट एंड VR2 इज द रिलेटिव वेलोसिटी एट आउटलेट। U जो है हमारा वो वेन की वेलोसिटी होगी। α1 जो है वो गाइड ब्लेड एंगल होगा इनलेट पे, α2 जो है गाइड ब्लेड एंगल होगा एग्जिट पे। β1 हमारा क्या होगा, β1 होगा हमारा ब्लेड एंगल इनलेट पे, और β2 हमारा क्या होगा, ब्लेड एंगल आउटलेट पे। ब्लेड एंगल कौन सा था, जो हमारा रिलेटिव वेलोसिटी और पेरिफेरल वेलोसिटी का हॉरिजॉन्टल एंगल था। और VU1 जो है वो VW1 जो था, जो हमारी एब्सोल्यूट वेलोसिटी थी, उसका हॉरिजॉन्टल कंपोनेंट जो था, व्हिच वी रेफर टू एज V1 cos alpha, that we call as velocity of whirl, which is the component of the absolute velocity V1 in the direction of the U, and VF1, which was the tangential component of the absolute velocity in the perpendicular direction, which we called as V1 sin alpha. It is called the velocity of flow, component of the absolute velocity V1 in the direction normal to that of U. Okay. तो वेलोसिटी ट्रायंगल जो हमारे तीन हो जाएंगे यहाँ पे अल्फा के तीन केसेस के लिए, 90 डिग्री से कम, 90 डिग्री के इक्वल और 90 डिग्री से ज़्यादा। व्हेन अल्फा 2 इज लेस देन 90 डिग्री, सो उस केस में जो हमारी फोर्स है, जो फोर्स होगी वो क्या होगा, रिलेटिव डिस्चार्ज इनटू चेंज इन द यू कंपोनेंट। जो हमारा वेन का जो हमारा वेलोसिटी है उसका जो कंपोनेंट होगा उनका डिफरेंस होगा। और उसके बाद क्या होगा, तो हम यहाँ पे यू कंपोनेंट का डिफरेंस चेक कर लेते हैं। इनिशियली क्या होगा, VU1 होगा, फाइनली क्या होगा, VU2 होगा। तो हमारा डिफरेंस क्या हो जाएगा, VU1 माइनस VU2। रिलेटिव डिस्चार्ज क्या होगा, QR इज इक्वल टू A इंटू VR1। सो हमारा फोर्स इन द एक्स डायरेक्शन इज इक्वल टू रो इंटू AVR1 इंटू VU1 प्लस VU2, जो कि हमारा ये आ जाएगा वर्क डन पर सेकेंड इज इक्वल टू पावर एक्सट्रैक्टेड फोर्स इंटू वेलोसिटी। सो पावर इज इक्वल टू रो AVR1 इंटू VU1 प्लस VU2 इंटू U। जब अल्फा जो है हमारा वो 90 डिग्री होगा, तो उस केस में क्या होगा कि जो हमारी जो एग्जिट पे, जो आउटलेट के केस में जो कि प्लेट की जो वेलोसिटी थी वो जीरो हो जाएगी। तो उस केस में हमारी पावर जो रो इंटू AVR1 इंटू VU इंटू यू हो जाएगा। और जब हमारा अल्फा 2 जो है वो 90 डिग्री से ज़्यादा होगा, तो उस केस में जो हमारी पावर है वो फाइनली कितनी हो जाएगी, ये हमने यहाँ पे इसको शो किया हुआ है। ठीक है। और यहाँ पे जब अल्फा हमारा लेस देन 90 डिग्री होगा, तब वहाँ पे हम पॉजिटिव साइन यूज करेंगे, और जब ग्रेटर देन 90 डिग्री होगा तो वहाँ पे नेगेटिव साइन यूज रहेगा। This was all from my side. Case 2 will be described in the next video by Naman Kumar. Thank you all. Thank you so much.
So hello guys, my name is Naman Kumar and my roll number is 165 and I am from Delhi Technical University and my branch is mechanical. And today my topic is tangential impingement of free jet on series of vanes. If the free jet impinges tangentially on a series of vanes, as for example vanes mounted on wheel, the entire discharge is intercepted by another vanes, and here the discharge is considered in equation 1.25c, and here is 1.25c. Yes, here we use the force in x direction, rho a VR1 multiply by VU1 plus minus VU2, and the equation 1.26c, here the power equation in the case where the water strikes tangentially in a series of vanes, not in series of vanes, only a single vane. So here we use the power as rho a VR1 multiply by VU1 plus minus VU2 multiply by U. So first of all we have to see the velocity diagram. तो velocity diagram देखना पड़ेगा, इसके लिए ऊपर देखते हैं एक बार. So here it is the velocity diagram. First we have the absolute velocity V1 and the relative velocity VR1. Let's get the terminology. V1 is absolute velocity of water at entry of the vane. VR1 is relative velocity of water with respect to vane at entry. U is equals to velocity of vane. In this case U equal to मतलब जो हमारे U1 and U2 है वो सेम है अल्फा, the guide vane angle at entry. It is the angle made by the absolute velocity v with the direction of the velocity of vane u at inlet, alpha 2. Guide vane angle at exit. It is the angle made by absolute velocity vector v with direction of velocity u at exit. Beta 1 is the blade angle at the inlet. It is the angle made by relative velocity v with the negative direction of velocity of the vane u at inlet, beta 2. Blade angle at outlet. It is the angle made by relative velocity v with the negative direction of velocity of vane u at the outlet. VU1, basically VU1 is the well velocity, the tangential component of the velocity, that in case of turbine that actually gives the velocity of wheel, component of the absolute velocity V1 in a direction of u. It is basically V1 cos alpha, and we can see through trigonometry here. Here we can see the wheel velocity Vf1. It is V2 sin alpha. V2 sin alpha, and basically Vf1 velocity of flow, component of absolute velocity in the direction normal, that of u, is equals to V1 sin alpha. Wheel velocity, yes. So move on to our topic, that is here it is, tangential impingement of free jet on series of vanes. So I want to show why we use V1 velocity, absolute velocity, instead of VR1. It is because the total discharge Q is equals to A times V1 and not the relative discharge. In this case, we are not using the relative discharge, we are using the total discharge in case of series of vanes, and in case of single vanes we are using relative velocity VR1. The relative equations of the total force in x direction and the power extracted by the values mounted on the wheel are. So basically here the force in x direction is equals to rho times A into V1. A into V1 here is the total discharge, and it gets multiplied by VU1 plus minus VU2. And why here is plus minus? Because if our angle beta is greater than 90, then we use negative sign, and if it is less than 90, then we use positive sign, and if it is 90, then VU2 become 0. So here it is written B, alternative expression for the efficiency of the case G2 when there is no energy loss. Oh, sorry. Yes, the efficiency of power transmission in series of vanes case, as defined earlier, the efficiency of jet impingement system is the ratio of power extracted to the total kinetic energy supplied to the vanes by jet. The total kinetic energy supplied by free jet per unit time is equals to E1 is equals to gamma A times V1 divided by V square by 2G. And here is our efficiency, neta is equals to P divided by E1, and here power we have just derived above, rho times AV1 multiplied by VU1 plus minus VU2 times U. So here it is power divided by E1. So our final expression is 2 times of VU1 plus minus VU2 multiplied by U divided by V1 square, with positive sign for alpha 2 is less than 90. For our case of not for series of vanes, for single vanes, our expression is comes out to be 2 times of VR1 multiplied by VU1 plus minus VU2 multiplied by U divided by V1 cube. So here we can see that V1 and VR1, we take total discharge, therefore our expression come out like this: 2 multiplied by VU1 plus minus VU2 U divided by V1 square. So here is alternate expression for efficiency of, and there is no energy loss. When there is no energy loss, because if there is friction on the surface, an alternate form expression of efficiency of the system could be obtained from the consideration of the kinetic energy of jet. Consider the set of series of vanes. The total power of the jet at inlet is E1 equal to gamma times Q multiplied by V square by 2G. Decrease in the power of the jet due to passage over the vanes is equals to power transferred vanes delta is equals to E1 minus E2 is equals to gamma times Q, and V1 square by 2G minus V2 square by 2G. The efficiency system is equals to power transmitted to the vane divided by kinetic energy supplied by the jet per unit time. And there is our expression. The final expression is bracket 1 minus V2 by V1 whole square. Yes. Summary. So we have earlier the two cases G1 and G2. G1 is when the water hits the vane tangentially, but there is no series of vanes. In case of G2, there are series of vanes. So here our expressions, you can see the similarities and dissimilarities. We can see that in case of G1, the fx is come out to be rho into A times VR1 multiplied by VU1 plus VU2. And in case of series of vanes, we just take the total discharge. So therefore we use the A times V1. The power is come out to be in case of G1 is rho A VR1 multiplied by VU1 plus VU2 multiplied by U. And in case of power of G2, so here we can easily understand that we just take the total discharge, and therefore the formulas are come out to be different. So as I told before, if alpha 2 is less than 0, we use the positive sign. If alpha is equal to 90, our VU2 component get vanishes. It becomes 0. If alpha 2 is greater than 90, then we use the negative sign. So here our next topic, mechanism of transfer of energy from water to a wheel. The impingement of jet of water on series of vanes mounted on a wheel is one of the mechanisms that been exploited in the transfer of energy of flowing water to the rotation of wheel. Such devices that extract energy from the flowing water are called turbines. Turbines that work on this impact principle are known as impulse turbine. As indicated in the previous section, Pelton turbine is an example of impulse turbine. The energy transfer from the water to a wheel can be achieved by another method. In this case, a cascade of properly shaped vanes are mounted inside a wheel. Water is admitted under pressure at entire periphery of the wheel. A set of fixed guide vanes help direct water to the vane cascade at predetermined angle. The water under pressure enters the set of curved vanes at the outer periphery in the tangential direction to the vanes and exists with the reduced pressure and velocity at the inner circumference of the wheel. While an impulse turbine is an easy to understand, the mechanism of reaction turbine is not intuitive. The principle of reaction of flowing water causing the motion of rotating element is illustrated in the following simple device. A revolving cylinder with the arrangement of inflow of water. Two arms of the bottom of the tank as shown in the figure discharge the water from the tank to the atmosphere through nozzles fitted at the end of arms. The change of pressure in the arms and the change in momentum of the flow cause a reaction force in the system. So here the system, a rotating device based on reaction principle. So this is the diagram, and this is the part axle, inflow of water, water level in the tank, rotation of the tank. So yes, the demonstration device figure 1.12 is known as Barker mill. After its inventor Robert Barker noticed that the Barker mill or in the common lawn sprinkler, the jet do not impinge on the runner. In fact, they are leaving the runner. It is the reaction of the exit of the jets that produces forces that result in torque to spin in the runner. Note that the direction of rotation of the runner is quite opposite to the direction of the jets of the water issuing from the nozzle. So here our topic ends. Thank you.
Hello everyone, my name is Raman Manav and my roll number is 2K20ME166. Today I am going to explain about the topic basic feature of hydraulic turbines. सो टरबाइन एक्चुअली होता क्या है? टरबाइन एक डिवाइस है जो कन्वर्ट करता है स्टोर्ड एनर्जी ऑफ अ फ्लूइड मास इनटू मैकेनिकल एनर्जी में. So depending upon the nature of fluid involved, we have different turbine like hydraulic turbine, gas turbine and steam turbine. So in a hydraulic turbine, the operating fluid is water and the energy of the fluid is a various combination of potential energy and kinetic energy. The turbine transforms this stored energy of water into rotation of a shaft through the medium of runner. तो ये दो डायग्राम जो है ये शो करता है. द फर्स्ट डायग्राम शोज द स्कीमेटिक स्केच ऑफ अ फ्रांसिस टर्बाइन and the second diagram shows the schematic sketch of a Kaplan turbine and generator set, and you can see different parts of these two turbines as they are shown here. So a modern hydraulic reaction turbine consists essentially of a rotating element called runner, which is acted upon by water. The runner will have a series of blades, appropriate casting and guide mechanism are provided to have efficient entry of water to the rotor. The blade of the rotor are so shaped that they have efficient interaction with the flowing water at the way from the inlet up to the exit. So as shown in the previous figure, that is 1.23a, you can see over the left side. Now we are talking about this thing. This shows the basic layout and component of a reaction turbine known as Francis turbine. So water from a penstoke enter the scroll casting, gets guided by the guides vane and passes through the passage between the blades of the runner. While doing so, the pressure of the water in the rotor changes. This type of turbine develops torque by reacting to the pressure of the fluid in a manner analogous to the rotation of a lawn sprinkler. The water that exits the runner passes through a divergent pipe known as draft tube and finally reaches the tail race. Another type of reaction turbine known as Kaplan turbine consists essentially of propeller acted upon the water under pressure. So as shown in the previous figure, that is the second one, a schematic sketch of Kaplan turbine. Now I'm telling about that. This shows the schematic diagram, the arrangement of such a turbine along with the generator. So in the next slide you can see the classification of turbine. The turbine is classified basically into two types, that is reaction turbine and the impulse turbine. And reaction turbine is subdivided into two types, that is Francis turbine, Kaplan and propeller turbine. And the impulse turbine is then divided into Pelton turbine. Now depending upon the nature of interaction with water flow, so we can subdivide these type of turbine into many parts, like they are broadly classified as impulse turbine and reaction turbine. The major difference in these two basic type of turbine can be summed up as given below. First one, I will tell about the impulse turbine. So in an impulse turbine, the pressure of water does not change while flowing through the rotor of the machine. In these turbine, the pressure change occur only in the nozzle of the machine and not in the rotor. The jet impingement take place at the atmospheric pressure. So an example of impulse turbine is the Pelton turbine, and now I will tell you about the reaction turbine. So in a reaction turbine, the pressure of water changes while it flows through the rotor of the machine. The change in water velocity and reduction in its pressure cause a reaction on the turbine blades. The flow passage and under pressure and the rotor has to be encased in airtight casing. Francis and Kaplan turbine fall in the category of reaction turbine. So here you can see different three type of turbine. That is, the first one is the Pelton turbine. The second diagram shows the Francis turbine, and third one is the of Kaplan turbine. Now, depending upon the nature of flow in the machine, the turbine could be classified as: first one is the radial flow, then the axial flow, then mixed flow, and the last one is tangential flow turbine. So in a radial flow turbine, the flow from inlet to the outlet of runner is along the radius. Inward radial flow is the most common feature. Early Francis turbine were of inward radial flow type. Now the second is tangential or peripheral flow turbine. The flow direction is tangential to the runner. Pelton wheel, where the path of the jet is tangential to the path of rotating wheel, is an example of this type. The third one is the mixed flow turbine. The water enters the rotor radially at the inlet and exit axially at the outlet. Present day Francis turbine is a typical example of this category. Now the last one is the axial flow turbine. In these, the flow enters and leaves rotor axially. The rotor blades of the turbine are essentially in the form of a propeller. The flow enters and leaves in a direction parallel to the axis of the shaft. Kaplan turbine, a turbine with adjustable propeller blades, is an example of axial flow turbine. Now the third one is depending upon the head. The turbine are classified based on the gross head as follows. The first one is the high head unit. For gross head greater than 400 meter are considered as the high head. Pelton turbine are usually the first choice for high head low discharge cases. The second one is the medium head units. It could be explained that the head greater than about 60 meter and less than 400 meter are considered as medium head. Francis turbine are commonly used in this range. The third one is the low head unit. In this, head is in the range of 3 meter to 60 meter and are classified as low head turbine. The fourth is the classification based not the fourth. The classification based on head is not a rigorous classification and is subjective. So depending upon the specific speed also it could be classified. Classification depend upon the specific speed is a better method than classification based on the head only. In this, both head and discharge are accounted for in an objective way. Detail of specific speed and its use are given in this table 1.3 is a brief summary of various type of turbine used under different range of speed. So the you can see in this table that there is specific speed of different kind of turbine given. And the fifth one is the classification according to the name of originator. Some of the name commonly associated with the turbine type originated by them are: first one is Francis turbine after name of James B. Francis. The second is Kaplan turbine, that is kept after the name of Victor Kaplan. The third one is Pelton turbine after Lester Allen Pelton. The fourth is Darius turbine after Paul Darius, and the fifth one is Banky or Michael turbine after Donald Banky and Anthony Michael. In this you can see the schematic layout of a reaction turbine. So this efficiency can be considered in three components. The first one is the volumetric efficiency, the second is the hydraulic efficiency, and the third one is the mechanical efficiency. So we will discuss all the three one by one. The first one, volumetric efficiency, it is possible that out of a total discharge of Q supplied to the turbine, some quantity of discharge Q1 supplied at the inlet of the turbine may exit the turbine in the form of various leaks without doing any work on the rotor. The volumetric efficiency of the turbine is defined as, here's a formula for finding the volumetric efficiency, which is discharge doing work on the rotor divided by discharge supplied to the rotor. Now generally leakage is a very small percentage of the discharge Q and is of the order of 0.5% only. The second one is the hydraulic efficiency. So while the net head H is available to the turbine, the energy head extracted by the turbine runner HE will be less than H by an amount of HF due fluid friction and from loss at the rotor, including entrance and exit loss at the rotor. Thus H is equal to H minus HF. The hydraulic efficiency of the turbine is given as head extracted by the rotor divided by net head available at the rotor. The third one is the mechanical efficiency. Due to the inevitable mechanical friction and occur between the rotor and other part of the turbine unit, such as bearing, glands, coupling, etc., and also due to presence of other mechanical losses such as windage losses where applicable, the power available at the rotor shaft will be less than the power produced by the runner. Let the head lost in mechanical friction and other losses be HM. The power transmitted by the turbine unit to the shaft is given as it is written over there, P is equal to gamma Q minus Q1 into HE minus HM. So the formula for mechanical efficiency is power available at the rotor shaft upon power produced by the runner. So that's all from our group. Thank you. Thanks a lot, everyone.